As we did in the last video, we want to come up with the equations we can use to help find the 5 parameters that define an object's motion: its displacement, its initial velocity, its final velocity, its acceleration, and the time. This time we're going to do it using the definitions of velocity and acceleration and some integration. Let's start with equation 1. Using the fact that the acceleration is defined as the rate of change of velocity with respect to time, dv dt, we can rearrange this and we can integrate both sides. We're going to integrate on the right side with respect to v, from v initial to v final. And on the left side, we're integrating with respect to time, from t initial, which is just 0, to t final, which we're just calling t. If we assume that a is constant, it comes out of the integral. The integral of dt is t, and we're evaluating from 0 to t final, which we're just calling t. On the right side, the integral of dv is v, our velocity, and we're integrating from v initial to v final. So when we evaluate our limits, we get at minus 0 on the left side of our equation, and v final minus v initial on the right side. Rearranging, we get equation 1. You might ask yourself, what happens if a is not constant? Well, if you're given the acceleration as a function of time, you can plug it into this equation. And instead of treating it like a constant and pulling it out of the integral, you plug it in, whatever function you're given, if it's a function of time, and you can integrate with respect to time. You'll get an equation that's a little more complicated than equation 1, but that's the way you would do it for a non-constant acceleration. Let's do equation 2 next. This is the trickiest one. Again, we'll start with our definition of acceleration, dv dt. But we're going to change this. We're going to write dv dt as dv dx dx dt. Mathematically, that's the same. I know you wouldn't think to do that off the top of your head, but it's a little trick we have to do on this one equation. The other equations are all more straightforward. Now we know that dx dt is our velocity. So we can write this as acceleration is velocity dv dx. We're going to rearrange this a little bit, bring the dx to the other side. We're going to integrate. We're integrating from v initial to v final on the right side of our equation. That integral is with respect to v. On the left side of our equation, our integral is with respect to x. So we'll integrate from x initial to x final. If a is constant, it comes out of the integral. The integral of dx is x, and we're evaluating from x initial to x final. And on the right side of the equation, the integral of v dv is v squared over 2, evaluated from v initial to v final. On the right side of our equation, we're going to get 1/2 v final squared minus v initial squared. Bringing the 2 to the other side, writing x final minus x initial as delta x, you can see we get equation 2. Again, if you ask yourself what happens if a is not constant, well, it doesn't come out of this integral if it's not constant. Maybe you're given the acceleration as a function of x. Maybe it changes with position. You could plug in whatever function you're given for the acceleration as a function of x, and then integrate it with respect to x, and you'd get a more complicated equation, but that's how you would solve it for a non-constant acceleration. In order to get equation 3, we're going to start with equation 1. We've already derived this one. V final is V initial plus AT. V is dx dt. I can bring my dt to the other side. V initial is just a constant, and we're going to treat a as a constant, so when we integrate both sides, on the left side I'm integrating over x, so I'm going from x initial to x final. On the right side I'm integrating over time, I'm going from t initial, which is 0, to t final, which I just call t. So I've got x evaluated for its limits. I've got v initial t plus a over 2 t squared, evaluated from t initial is 0 to t final is t. This gives me x final minus x initial, v initial t plus 1/2 a t squared minus 0. And I'll write x final minus x initial as displacement, change in x. And there we have equation 3. Equation 4 is perhaps the easiest one. We're going to use the fact that the average velocity is just displacement over time. And we also know that the average velocity is going to be v final plus v initial over 2. We're averaging v final and v initial to get the average velocity. If the acceleration is constant, the velocity is linear, and we can find v average just by averaging the endpoints. If v wasn't linear, if it had some curvature to it, we couldn't do this. But this is true if the acceleration's constant. Well, we just set these two equal to each other. And we end up with equation 4. Up until this point, we've just been doing graphical kinematics problems. Now you see where these equations come from, and in the next video, we'll do a problem using the equations.